Hello everyone, welcome back to my channel Beyond Future. The topic which I am going to talk today about is polar coding. Contents which I will be focusing on are polar coding, encoding, decoding, its implementation and its simulation. The polar codes were first invented by Erdal Arıkan in 2008 based on the idea of channel polarization. What basically is polarization is that we divide the channels from the worst to the least, from the worst to the best performance, or from the worst bits from the worst performance or the weak channels to the most strong channels, which we can use to polarize our bits. These codes are first to have explicit proof of approaching capacity, which are sequential in nature, as you will know later in the slides that why these are sequential in nature, and they are basically defined using a generator matrix known as the recursive or kernel G matrix, and the product we use for that matrix is chronicle product. You can relate to its importance from the fact that these are the first ECC codes or error correcting codes which achieve the Shannon limit, which is a reliable transmission of information and at rates up to the capacity of channel. Its encoding and decoding time complexity is O n log of n, and it can achieve channel capacity for discrete memoryless channels. Memoryless channels are basically those channels in which only we can just save or store the current bit. After that bit is passed on, there is no previous bit stored in that channel. So let me tell you about how these codes are implemented and why they are being used in 5Gs, just because of the fact of the sequence reliability of these channels that is due to its polarization technique. We have channels with worst and best qualities. The best quality channels are chosen to send or transmit the bits at the receiver side. So how these codes are implemented is that over here you can see that G2 is a kernel matrix with 1101 as the matrix as the matrix inputs, and then over here we have at the input u1 and u2. As you can see from binary tree representation, let's suppose that u1 and u2 at the leaf nodes are basically the binary bits, and these binary bits are connected by the parent node, that is u of 2. So the formula which we use over here is that we perform XOR on the input bits, and the second bit that you get at the parent node is the same as the second input bit. So let me give you an example. If you want to transmit 0 as U1 and 0 as U2, as you can see here in the XOR table, we have to perform XOR on the first bit. U1 plus U2 is basically we are performing over here the XOR, and the U2, that the second bit we will have at the parent node, is the same bit as the second bit we transmitted earlier. So if we are sending U1 and U2 0 as input bits at the output U1 plus U2, when we perform XOR, U1 plus U2 becomes 0, and then U2 is equal to 0. And then if we are perform at U1 you have 0 as the input bit, and at U2 you have 1 as the input bit. At the output or at the parent node you will have 1 1 as the output polar encoded bits, and so on. Over here you can see the previously we have seen that what happens or how the polar transform is done or polar encoding is done when we have two bits at the input. Practically this is not the case. So over here for the G4 kernel matrix you have to, so for the G4 kernel matrix our matrix becomes of the form 4 cross 4, and over here you can see that G2 into G2, we take its chronicle product, and at the output we get a 4 cross 4 matrix. How we are performing multiplication over here or the chronicle product over here, the chronicle product has this general or has this general formula you can say, or this is basically a trait or quality of the chronicle product, that what happens is that just you have to imagine that in the first, that the G2 kernel matrix is multiplied with the first bit, first row of the first column of the second matrix, and that whole matrix is repeated in the G4 2 cross 2 2 cross 2 first column, and second column, first row and second row matrix. We are repeating, there are three ones as you can see in G2 matrix. We have in the first row and first column one, in the first row and in the second row and first column one, and then similarly in the second row and second column we have one. So the matrix G2 is repeated three times in G4, and where we have 0 on the left, on the right, top right, so the zeros are repeated similarly in our polar transform G4. So what is happening over here is that what we do in it is, as you can see in the bullets I have mentioned, that we have to, let's suppose that we want to perform polar transform on four input bits u1, ut, u2, u3, u4. These four bits are uh, these four bits are these four bits are multiplied with the kernel matrix for G4 cross 4 G4, and what we have at the output is u1 plus u2 plus u3 plus u4. Similarly, u2 plus u4, then u3 plus u4 and u4. Since I have not mentioned until now what is its binary tree representation, this picture will become clear to you in the incoming slides. And similarly, if you have 8 bits at the input and you want to perform polar transform on it, the output, you can see that the output is, we have 8 bits at the output with XOR performed, and the 8th bit the same as the as what we did in the previous example. So this is the binary tree representation of the G4 of for the 4 bits and the matrix G4 that we use to perform XOR. Over here you can see that we have 4 input bits u1, u2, u3, u4. What is happening here is that at u1 and u2 and then at u3 and u4, you are performing uh, for performing polar transform with the G2 matrix, and after performing polar transform you are storing that value at the interior nodes, and then after those interior nodes at u2 u of 2 subscript 1 and u of 2 subscript 2, these again you are performing polar transform on these both bits and storing it in u of 2 1 plus u of 2 XOR on it, and then u of 2 of 2. So how this is happening is, what we are doing over here is that let's perform XOR and the polar transform on u1 and u2. What you get at the interior node is u1 plus u2 as the first bit, and then u2 as the second bit, which is polar transformed. And then on the other hand, say the same is performed on u3 and u4. What you're getting at the interior node is u3 plus u4 and then u4. And so after performing the polar transform on both these bits, so let me be clear that at the leaf node, you had two single bits. Each node stored single bits. Then, as you moved up the hierarchy, there were two bits stored. And similarly, when you will move up the hierarchy, there will be four bits stored. So now you're performing the polar transform on u of 2 subscript 1 and u of 2 subscript 2. So what you are doing over here is that we have u1 plus u2 and u2 stored at u of 2 subscript 1, and then we have u3 plus u4 and u4 stored at this u of 2 subscript 2. What you are doing over here, you are combining both of these, you are implementing the formula, and then you are storing these values at the parent node or the fully polar transform code for the 4 bits. So let us perform let us perform on these both bits. What happens over here is you have to first perform polar transform on the first bits, so u1 plus u2 plus u3 plus u4, then you will have u2 plus u4, and then you will have u3 plus u4. After that, u of 2, that will be u of 4. So this is how you will perform polar transform in a 4-bit for the 4 bits input bits. You will encode the it using this polar transform. So this is the polar transform for G8. As I have told you earlier, the highlighted or bold, the highlighted area, the highlighted numbers with blue, you can see that 10110, this whole highlighted area is basically G4, and it is being repeated 4 times to make an 8 cross 8 matrix. It is repeated 3 times with 1, and when there you have at the top right, at the top right, when you have 0, you will multiply the whole matrix with 0, and it becomes 4 cross 4 0 at the top right in the G8 corner. So this is the binary tree representation for the G8 matrix. The repetition of the previous steps will be followed here to get 8 bits encoded polar code, and so on as we increase the n. For example, for 2 raised to power 1 we had 2 bits, then 2 raised to power 2 we performed polar transform for 4 bits, then 2 raised to power 3 we performed polar transform for 8 bits, and over here you can see that we have a depth of 3. So as the number of n increases, our depth increases similarly. So this is the general formula of polar transform. The previous were the examples. Over here you can see that we have a general matrix G2 raised to power n. Now, talking about the general picture, we can see over here that we have capital N is equal to 2 raised to power small n, and then we have Gn n cross n matrix Kronecker product of 2 cross 2 kernel. Then there's binary tree representation with depth raised to the with depth of small n, and then we have u of n at the top, which is u into g of n evaluated on tree with u at the bottom. And as we all know that 5g uses up to 10, up to n is equal to 10. So what is happening here is that the small n, or you can have the Kronecker products of G2 into G2 into G2. These are basically the Kronecker products. If you want to achieve the if you want to have the G or G8, then what you are going to do is that you have to take the previous, which we calculated, G2 Kronecker product G2 Kronecker product G2. That is what it means, is basically that we are having the Kronecker product of G n times. As you can see over here that we have the G2 matrix raised to the Kronecker product of n. This is equal to basically G2 Kronecker product into G2 Kronecker product G2 raised until n times. So over here you can see that bigger n, or the capital N, is equal to 2 raised to power small n. So for the bits 2, 4, 8, 16, 32, and so on, that is, if you are inputting two bits, you are getting two polar encoded bits at the output. And similarly, when you input 4 bits, then you are getting 4 output bits, and when you are inputting 8 input bits, then you are getting polar encoded 8 output bits, and so on. As we discussed earlier, depth n is basically the hierarchy of how we are performing how we are performing polar transform on the tree, and the hierarchies of the system, the levels that we have in the tree. There are leaf nodes, then the interior nodes, and then there's the root node after the interior nodes. And over here, there is a small fact that I have written over here, that is that 5G uses up to n is equal to 10, which means that in 5G technology that which we are going to use, we have small n is equal to 10, which is currently being used over here. So n comma k polar code. What we are doing over here is that let's suppose that we have the message m of length k bits. What we are going to do is that we are going to form a vector of length n bits, and what we will do over here is that we will subtract k from n, which means that we are basically polarizing the channels. We are following a reliability sequence. We are polarizing the channels from worst to best possible performance of these channels. And what we do over here is that when we polarize the channels, for example, let's suppose that we have n is equal to 8 and k is equal to 4. What we're doing is 8 minus 4 is equal to 4. So we have the 4 bit positions, or 4 channels, where we will uh, put ui is equal to 0, and the remaining bits we have, those are our message positions. Let me give you an example. Over here we have two examples. The first one example is of 16 comma 10. Over here n is 16 and we have 10 message bits because k is equal to 10. What we are going to do is we are going to freeze the six positions, the first in the reliability first six channels or the first six bit positions we are going to freeze, and in the other bits or other positions or other channels we will have our messages stored. So you can see that one over here 1 2 3 5 9 4 6 10 and so on. This is our basically reliability sequence. Let's not get into the nitty-gritty task of how the reliability sequence is performed. There are many research papers you can find online of about it, that how these channels are characterized or polarized and how they perform from worst to best possible conditions or performances. So what we are doing here is we are freezing bit 1, bit 2, bit 3, bit 5, bit 9 and bit 4, and then at the 6th, 10th, 7th, 11th, 13th, 8th, 12th, 14th, 15th and 16th positions we have our message stored. So to make it a little easier for you, I am going to give you an example for the 8, 4 polar coding. Over here we have our reliability sequence as 1 2 3 5 4 6 7 8, which means we 8 minus 4 we have 4 bits we have to freeze. So what we are going to do is, since the first channel or the reliability sequence works as the first bit is the worst, or first bit or first channel is the worst, and as we move on in the reliability sequence our performance gets better and better and better to the last. So what is happening over here is that we are freezing first, second, third and fifth bits, and then our message is being stored on the fourth, sixth, seventh and eighth bits, and then we are performing our polar transform on it. So starting from the leaf nodes, as you can see that we have first, second, third and fifth nodes frozen. So the 0 is stored here, since this is the rule that the bits which are frozen, you should store 0 there. After that you are performing the polar transform on the first bits. You know that since we have both zeros over here, so u subscript 2, u of 2 subscript 1, over here we will have one stored as XOR. We will have two bits stored, 1 and 0, and at the u of 2, u at the depth 2, at the u of 2 at subscript 2 and depth is equal to 1. Over here we will have stored, we will first perform our 0 plus m1 XOR, and then we will have m1 stored in the second bit position, and so on. As we move up the depths, our bits will also increase. At the leaf nodes we have one bit in one node. As we are moving up the level we will have two bits stored. As we are moving up u raised u of 4 subscript 1, over here we have 4 bits stored, and at the u of 8 we have 8 bits stored. This is basically the subscript you are seeing. Basically this also denotes the number of bits stored at each node. So since you have gotten a little bit idea of how polar encoding is performed, let's move towards polar decoding using successive cancellation. What happens is in polar decoding is that you know that when you receive a message, you have a polar encoded message, you have received it at the receiver. At the receiver your message is basically the beliefs we have that what basically we could have received. So the bits which are believed that we have received from the encoder, what we do is that we at the root those nodes are those believed bits are stored, and what we do, we perform three operations, that is step L, step R and step U. What happens in step L is that whatever the bits are stored at the root, you split those bits in half and you send it to the left child. Then the function is performed at the left nodes or the left interior nodes or the left child node or the leaf node, and after performing that function what happens is that we receive u hat of one bit of m by u hat of 1 which are basically m by 2 bits back at the interior node. And what happens is that we use we use that u hat of 1 for our step r, which is the operation to be performed on the right nodes or the right child nodes. Then what happens is that after getting the value or the u hat of 2 supposed from the right child, what happens is that we perform the step u. Step u is the same as that we performed for the polar encoding, that is u hat 1 plus u hat of 2 and the believed u2. So how are we going to proceed in it further is like this. These are the steps. What happens is that we start at the root. At root, this is the depth first tree traversal method which I am going to discuss. We start at root. We have number of believed bits at the root. What happens is that we go to step L, which is here where we perform the min sum operation, and we go to the left child. When the decision is received from the left child, I will discuss about what kind of decisions we make at the left child. So in the later slides, so what happens is that when a decision is received from the left child, we send that decision up via u hat of 1, and we do step r, which is the combination, repetition and decision step, which happens at the right node or at the right child. So after, when the decision is also received from the right child in the form of u hat of 2, we do step u, which is basically u hat of 1 plus u hat of 2 and u2, the same polar encoded step we did, but this time for the believed values or the received values which we think we may have received, and then we go to the parent. If there is the leaf node, we make decisions. When we approach the leaf node, then we make this decision, and afterwards we go to the parent. So what happens in the leaf node, the decisions which are taken in the leaf node are, if the ith is the position or the ith is the frozen position, then u hat of I is equal to 0. This is an evident fact. We saw earlier that in the reliability sequence, when we have to freeze the bits, they are termed at 0. So you have to ultimately term those bits 0. So if I is a message position, so if u hat of I is equal to 0, then the operations that you have, if by operating the functions at left of u of I, those operations are greater than or equal to 0, then u hat of I that we receive is equal to 0. And if L of ui is less than 0, then the u hat that we receive is equal to 1. That is the message we receive, or the bit we receive is 1 at that position. That may be a little confusing, but let me make you clear by this example. Let's suppose that R1 and R2 are basically two bits that we have received. We don't know that if both bits are 0, if one is 0 and one is 1, and if both are 1 and if both are 0. What happens here is that R1 and R2 are stored at the root node. What we do in the first step, we have to move to the left child, right? So what we are doing here is we are splitting the stored bits, and we are moving towards the left child. So in the left child, after moving towards the left child, what we have to do is we have to perform L. Over here, L is f of r1 comma r2. As you can see here, I have written a statement. What over here is that sign of first bit is multiplied by sign of second bit, and these two signs, after multiplication of these two signs, a min sum is performed on r1 and r2. Those are the realized bits. So after performing this function, we send that bit u hat of 1 back to the parent. So in the second step, what happens is that after the u hat of 1 is received by the root, we send R1, R2 and U hat of 1 under G function to the right child, and we perform the function over there. What happens at the right child is the function we perform over here is that R2 plus 1 minus 2b into R1 is performed there. and the value is assumed to be u hat of 2 and then sent back to the parent node again. So after receiving u hat of 1 and u hat of 2 from both the left and right child simultaneously, what happens is that the polar transform is performed. U hat of 1 plus u hat of 2 and u hat of 2 are stored in our hat of x. That is the realized value. So x1 is basically the u hat of 1 plus u hat of 2 and x2 becomes the u hat of 2 by performing these basic functions on the polar code that we have, or the bits that we have received. So over here, this is a simple decoding for n is equal to 2. Over here, let's see the block diagram. In the block diagram, you can see that we are sending two bits u1 and u2. We have performed polar coding on this. These bits are encoded and are now termed as x1 and x2. Then what happens is that we have to pass them through a channel. We are passing them through the channel. We perform binary phase shifting, modulate them through BPSK, and then the noise is introduced in the channel, because realistically we know that in the practical channels there is the noise. So after the noise, the addition of noise and BPSK, we are receiving two bits in the form of R1 and R2. So what happens is that we have to move from R1 is considered as x1 and R1 is considered as x1 plus x2, R2 is x2, and then so forth. We have to move backward to get the our authentic, or the bits we sent, not the realistic bits that we had sent via the transmitter. So you can see over here on the right now that there's binary tree representation, how we perform the operations step L R U, and after doing those operations receive we can reach to the conclusion of u1 plus u2 and u2. There's the certain threshold and the decisions we have to make at the leaf node, at the L, at the R, so that we can realize what basically we sent, or what were the after the polar, before polar coding, what were the bits that we sent in the system, so we can decode it similarly. So this is another steps we can take for decoding for n is equal to 2. Over here we have soft input soft output decode u1 first spc. Spc is basically single parity check. This is used for the most of the decoders, and then there is the repetition to decode u2. So what over here happening is that at the left node u1, at the left, at when we are performing L at u1, we what we do is that the realized or the believed bits R1 and R2, we take those bits, we perform f of R1 and R2 on it, we take the sign of R1 and sign of R2, because we know that in BPSK that 0 is mapped onto positive 1 and 1 is mapped onto negative 1. What happens here is that the R1 and R2 are basically the bits after going through the modulation and going through AWGN channel. So what happens is that the signs of those received bits are two received bits are multiplied and the min sum is performed. And if the min sum performed is greater than, if the whole function performed on the bit is greater than or equal to 0, then u hat of 1 is equal to 0. And if the min sum performed and the min sum performed and after going through the signs, multiplying the signs, going through the whole function, if the L of u1 is less than 0, then u hat of 1 is equal to 1. So after getting u hat of 1, we decode u2. We can only keep in mind that we can only decode u2 after we have decoded u1. We have to go sequentially in decoding, not parallel like we do in LDPC codes. So if u hat, what happens next is, if u hat of 1 is equal to 0, then L of u2 is r2 plus r1, then we get x is equal to u2. But if u hat of 1 is equal to 1, then L of u2 is r2 minus r1, and at x, that is the bits that we have come to realize that may have been forwarded to us, are that x becomes the x is equal to u2 complement and simple u2. So this is another example with 16 bits stored at the parent node. This is another example of the successive cancellation decoder in which we have 16 bits, believed bits, the bits we have received from the transmitter at the root node. What we are doing is over here is in the first step, we split these bits and go to the left child. The bits are split in the first step and the 8 bits are sent to the left child. So you can see over here that L raised to the power 8 or L of 8, over here we have stored 8 bits, and on the right you can see L of 8, 8 bits are sent towards the right node and 8 bits are sent toward the left node successively. After going through after the first step, we have second step, that is 2L. Over here we have again split the bits in the two parts. 4 bits are again sent to the left child. The process goes on and on until we reach the fourth step where we perform the decoding, or where we perform basically the steps or the or the operations, that is L, R and U operations, which I told you earlier. Over here I have not shown the U steps because it would have been a clutter. You can get a wage picture of what over here is happening is, since we are going to send 16 bits, so this is the six bits are frozen. Because of the reliability sequence, we have 10 message bits and 6 bits are frozen, and n is equal to 16 for this case. So at the first, second, third, fourth, and fifth, and similarly at the ninth position, we have bits, frozen bits equals 0. But what's happening over here is, let's start from the fourth step forward. After performing L at the fourth step, we are sending U hat of 1 at the at the node above it, that is L of 1. After sending U hat of 1 over there, we go to the we start perform the right step. In the right step, that is the fifth step or 5R as seen over here, we perform the right functions or the operations we have to perform at the right node. And what happens is that we send u hat of 2, that is the realized u hat of 2, back to the interior node and perform the u operation on it. After performing u operation on it, then we go at sixth step and we send at the sixth step again we perform the L operation, then we perform the R operation, and then we perform the U operation of polar transform, and so forth. And we go on like this and traverse the whole tree to get the decoding of the polar coded message we have. This is the simulation of the polar codes. Over here, as you can see, at the input at the input bits that I have sent are 0010, and the encoded input that we are getting is 11111000. And as you can see above, a is equal to 00101111. This is basically the reliability sequence. We are sending 4 bits, then we are what we are doing is that we are encoding this input, and at the received output we have the bits. Over here you can see that we have received two NANs. This can mean that there may be a problem while sending the bits through the channel, and at the decoded output you can again have 0010 via the successive cancellation decoding I have discussed previously. So the transmission over here that I have is that if the decoding and encoding is performed successfully, then it should show the message of success. If not, then it should show the message of failure. For this presentation, and the references which I have used are these. So and let's meet in the next presentation.